And SIE is the Security Information Exchange, which is kind of a more or less free-ish way to get, Paul will kill me later, to get access to a bunch of data, which includes things like passive DNS and spam feeds and things like this. Eric Ziegast is a ISC.
It's a program manager for SIE.
This
is my day job.
Ah, okay, good. And Paul Vixie is one of the ISC founder folk and here to supervise, I suppose, right?
Yeah. General White Hat.
You betcha.
Okay.
All right. So SIE, Security Information Exchange. People are familiar with different kinds of exchanges. You'll have exchanges of money on like NASDAQ. You'll have internet exchanges, which Paul actually founded one of them, Palo Alto Internet Exchange, where they needed to exchange internet traffic. And they may exchange pieces of copper between all the telco, or fiber these days, between all the telco gear. Back in 2007, Paul Vixie, David Dagan kind of thought up this idea that there's a lot of pooled data out there that a lot of people don't have access to, and we need to find a way to get it all together. So one of the things that we're doing, because this is security data, people don't like sharing it because they can get in trouble for it because either they're snooping on their customers or because it can cause harm to people just because of the fact that someone knows something that they shouldn't have. So what we've created is a legal and privacy framework, which is basically a contract and a bunch of privacy directives to say, all right, everyone is in this together. You can share stuff freely within the infrastructure, but you don't take the raw stuff out. It has to go through lots of processing before you can take stuff out of there. And the legal document keeps everyone honest. Another reason we're here is to centralize the data collection. When you have pools of data that are all over the internet, it's hard to do any cross-correlation. You don't have any standard way of sharing the data. They have different formats. If you can get all the formats the same and you can get all the data together in one data center, or within a framework of data centers all connected to each other, there's a better chance that you're actually going to be able to do some cross-analysis, which is one of the things we're trying to do. You may have some passive DNS, you may have some NetFlow, you may have some darknet data or whatever you have, but if that's all you have, you're not going to be able to do much with it. But if you can combine some of that, you're going to be able to find out a lot more and find it out a lot more quickly than if you don't have access to it all. One of the reasons we're doing this is to create a network effect between the security researchers. One model can suggest that it's like stone soup. Ever heard the parable? We're bringing the soup and the stone, which includes our infrastructure and the network and the tools that we have. And then a lot of people are bringing their carrots and onions and potatoes to make it taste better. And the more people who add stuff, the better tasting the soup gets. And eventually, you can actually do some really effective work with it. Typically these days you have relationships between these various participants, businesses, ISPs, law enforcement. The people on the top typically have some of the data, or they're the victims, and the people at the bottom usually have the ability to do something with it, and they all have their own independent non-disclosure agreements, contracts, whatever you need to manage to keep everything private and functional and keep everyone honest. That's a lot of paperwork, and it's a lot of trust that has to be built up between people, and it's inefficient. So one of the things we're doing with SIE is to create the efficient sharing within a common legal and privacy framework. People can bring their data into SIE, have it be sort of a clearinghouse in a place where it's all available freely, and you can share freely within there, and you can sign a single agreement that everyone else signs, and everyone can work within SIE. We're not going to replace everyone's sharing. We're just helping to enable things which might be inefficient right now. Typically for the infrastructure, we have a bunch of sensor operators out there. You know, it might be something sniffing packets off the wire. It might be something attached to your mail server that the spam flows into, or you know, you have a web crawler and you're going out searching, but you just go ahead and create, we're basically packetized bundles, and they all get uploaded via rsync and some scripts that to our redundant servers, so that we can broadcast that onto an Ethernet infrastructure within a data center. Inside of that broadcast infrastructure are a bunch of researchers who all bring their own machines and hopefully some of their own data to compare against. As we build out, we're going to build a node on the East Coast, and we'll relay data between the nodes. And additionally, each of the researchers will be able to talk to each other over the private network. And as we add other areas, like for example, go into Europe or Asia or wherever, we may add a relay where people can upload stuff into the cloud. And at some point, oh boy, I used a wonderful, there's that cloud thing. Let's strike that. We have relays where the data can enter, and at some point it may get promoted so that it can talk to all of the rest of the nodes on an equal basis, and we basically take any of the unique data that's going from one area and pass it to the other so the others can see it. It may not be all the data. There's a lot of data, and a lot of it doesn't need to get shared, but maybe some of the aggregate stuff will get shared between the nodes. Here's some of the types of data that is out there. We started with passive DNS and DNS blacklist data. We have some darknet and NetFlow, but there's a lot of other different types of data which aren't necessarily conducive to plain old packet captures. And we had to invent something so that we can describe these various types of data so that they can be efficiently shared on the broadcast network. The first thing we worked with was passive DNS. Florian Weimer out of Germany, he pioneered the capturing, and we modified some tools so we can do a better job of collecting it on the name servers to collect more of the data. Typically with passive DNS is, at least the way that we collect it, is you have a name server, and your clients all go out through a recursive name server or caching server to find out the names that you're looking up. You're looking up www.google.com. Well, the client's not going to talk to the Google name servers. They're going to talk to a recursor at their ISP. That recursor sends a request out to the com name servers, to google.com name servers, and then they all feed the data back to the recursive server, and then once the answer is found, the recursive server returns that to the client. The position where we listen is on the downward arrows that are going back to the recursive name server. There's a great benefit to that in that it helps enable the privacy of the clients, because the recursive name server is doing the queries at that level, not the clients. So if you have a large population, say 1,000 people or 1,000,000 people, you won't necessarily who's making the query, but you'll at least find out the information that's out there. And that's part of the goal, is to actually get a better map of what's out there as far as IP addresses, mapping to names, mapping to name servers, to get a better map of what's out there that you would not normally see if you didn't have these sensors out there. So we asked a bunch of ISPs and universities and friends to donate some data, and we're very appreciative of that. And we have been building up and trying to get more data and more data types from different sources. The main way to do DNS data collection back then was TCP dump or DNS cap. There were some inadequacies in those programs that they couldn't capture everything. So we created a new program called NCAP, an NCAP tool. And added a bunch of features into that so that you could replicate the passive DNS data into the broadcast infrastructure that we were setting up. We added some features for doing plugins, so you can do filtering on the data as it passes into one. You can filter out the things that you don't need to see so that you can spend more time processing the data that you want. For the other data types, for example, spam or link pairs or malware or whatever, we created nmessage, and we'll get to that later. Also, to enable some collaboration between the researchers, we set up a VPN between our sites so that researchers at one site can talk to another using unicast. Basically, your typical access a web server or a database or whois or DNS lookups or whatever. But it's all private within the framework. Some of the hardware that we need for this needs to handle high packet rates. You need a fast switch that won't drop packets. The servers will typically be 64-bit with a lot of RAM, and your storage, if all you're doing is logging, disk is fine, but if you want to do anything active with it, you're going to need SSD or a lot more RAM because there are high packet rates for a lot of what we're dealing with. NCAP tool. Here are some of the things that we did to improve upon PCAP or DNS cap. With larger DNS packets these days, you actually have fragments. That is, what used to be able to fit in 512 bytes doesn't fit anymore, especially if we're doing things like DNSSEC and increasing the number of servers and the amount of data that's coming back with each of these requests. So we need to be able to reassemble the packets, and NCAP does that automatically, whereas you might actually miss that data if you're using just PCAP. We dropped the link layer info. We don't need to care about the Ethernet MAC address. We're just really interested in layer 3 and above. Normalize the network format so that what we collect on a SUN will work on OpenBSD on a PC, will work on an HP, running RISC. Just basically the network byte order. Nanosecond timestamps instead of millisecond, and then added some user-defined flags so we can actually track what was the sensor that actually gave us the data. What's key to SIE is the fact that we have this common infrastructure where everyone can listen to an Ethernet bus of the same data. So when it comes into one of our nodes, we will rebroadcast it on a local area network on a VLAN, and everyone who's on that VLAN will get that packet at the same time. So it's not like we're just sending it to each researcher, we're actually just broadcasting it, and that makes for a lot of efficiencies. And we need to be able to take data from files or put them out to files, and we can do all sorts of passing the packets. Once we have the packets, we can ship them around in many different ways. One of the best benefits we had of NCAP was when we started making modules to do deduplication, which was very necessary, some pattern matching, internal database lookups, like if you want to match what you're seeing off of the wire against an internal table of something that you know. And that was really important. Typically when people are setting up security or doing security data gathering, they'll put everything into a database and it may not scale. At some point they'll become disk bound, and we need to be able to keep the information flowing in real time and not just being trapped into a database, which will eventually slow down. And we can't just log the data because it's really not useful. People need to create real-time tools to be able to analyze that on the fly. What we ended up doing is we built called a loosely coupled multiprocessor, where one machine would actually start out with the data, broadcast it onto the network, another machine would do some different processing, and then once that machine does processing, it would broadcast it back out onto the network, and then a bunch of other machines would be interested in that, and they'd do further processing. So you have a bunch of machines all together on the same broadcast network, and they're all doing the processing in real time. And I'll have a diagram describing that more. We partition our data, like for the various data types, into different VLANs. So you got passive DNS on one, deduplicated passive DNS on another. You'll have some NetFlow on one, you'll have some spam on another. And then you can choose which VLANs or channels that you want to subscribe to, to cut down on your overhead of what you have to process. So this is a typical use of a filter, where the data is coming in on the left. This is the raw, say, passive DNS data that's coming in from the sensors. It's at a very high rate of speed. We have a program which operates on a server, runs completely out of RAM, that does a deduplication of what's in there. You may have 100 people looking up www.google.com, but you don't really care about that. You're really interested in the fact that www.google.com is out there, and here's the information that came with it. So deduplication takes it down to a reasonable level where people can actually do the processing with it. And then you can do some additional filtering, like we have something that helps detect fast flux. Fast flux, in one example, would be, say, when your name servers keep changing their IP addresses. That's very useful for helping to detect botnets because that is one of the behaviors that they use. So this is a graph from last night where you get about 40,000 packets per second. And that's like somewhere around 80 to 100 megabits of all just DNS packets. And to do any real analysis with it, unless you got 20 or 40 servers that can kind of split or take a part of that feed off of it, it's really going to be inefficient to process. So we do the deduplication. Pardon the graph, but just look at the numbers. That now you're down to about 5,000 packets per second, which is a little bit easier to process. It's like an 8-to-1. We're getting about an 8-to-1 benefit out of our deduplication, and it lasts about every 4 hours. It'll roll over for fresh data, so it gives you an idea of how that works. And then just for finding fast flux, well, we get about 2 to 4 packets a second of just things that are changing in fast flux, and you can actually just watch that stuff scroll by on the screen and use your human intelligence to figure stuff out. Like, if you have like a bank phishing site and it's changing its name servers, well, you just see it scroll by on the screen and say, hey, there's a domain I'm interested in. The concept of loosely coupled multiprocessor is very important. Dave Boggs was doing this at Xerox PARC and DEC back in the 80s when they invented Ethernet. A lot of people were just using it as, here's I get my packets from A to B, but he was starting to use methods to actually use broadcast, so you can actually take one piece of data and broadcast it out to multiple servers efficiently. And another feature of this is that we're leaning toward real-time analysis. A lot of people in the research field these days, they build their big databases and they do queries against the databases. Well, if instead, if you do that and it's taking too long, the bad guys, they're moving on after a few hours, and if it's going to take you a whole day to figure out something, well, you're pretty much losing. So if you can basically find ways to put the stuff into RAM, you can compare it with what's out on the feed, and you can actually give yourself an advantage. Do you want to say anything more about what Alex did?
Some of this isn't new, except it's what's old is new again, because the way this kind of thing used to work when computers were fast and the real world was slow, or computers were fast enough, is you put in a database trigger so that everything got dumped to the database, but then when certain things, certain lines would cross, then you would learn, okay, you just tried to put something into the database that caused the following exceptional behavior, you should analyze this. And certainly in the case of SQL, there's no way you're going to keep up with even 5,000 per second, let alone hundreds of thousands of things per second if there are triggers in place. And all the SSD in the world isn't going to help you do that. So I will say that this is, to me, the money bullet point in this presentation is that the security community has gotten into the habit of storing PCAP files or storing things in database tables and then having cron jobs that go look for things, and we are not keeping up. The bad guys are winning. I'm tired of that. So the idea of teaching people once again how to look at things in real time and look for cross correlations in real time was at the heart of this project originally.
There is some benefit to analysis in arrears in that you can perhaps go back and look for things that would help you change your patterns or what you're looking for in real time. Just much like a stock analyst would look at their historical trends of a stock to try to predict what's going on in the future. Well, at some point you have to have something automated that's pulling that trigger for you to buy or sell, and that's perhaps some of the kind of analysis we'd be doing for internet security data. So here are some of the things that we've got on SIE right now. Raw passive DNS is what comes in from the sensors, and then we filter it out. FastFlux is one example. We do some comparisons to some things like CBL or Swords, Spamhaus CBL. That's interesting because you may know the IP address of something that's bad, but you don't necessarily know all the names it's using. So using this, you can actually, in real time, gather all the names that are being used by a particular machine or that people are looking up against it. Helps you do some cross-correlation and preventive work. We gather some DNS queries from some DNS blacklists, from dynamic DNS providers. Some top-level domains, we put isc.org in there. AS112 is a project where all the stuff that shouldn't leak out for DNS lookup, someone looking up 10.inaddr.arpa, for example, or something within there, well, that's basically misconfigured networks or name servers out there. And some of the root servers, which no longer operate, they still have an IP address that people see in the query, so we're gathering a little bit of that too. We don't gather root servers. We operate our own root servers, but we actually have a firewall between us and them. And a lot of that analysis is actually goes out to DNSOARC. So NCAP was great for packet data, but there's more that we need to capture. It needs to be extensible. That was maybe a mistake we made with NCAP when we set out. We didn't put version numbers in there. We need to be able to create new formats as new data becomes available. It needs to be fast and scalable. If you're looking to describe this stuff, you can imagine, let's just use XML. Well, that doesn't work very well. That's part of why we're here at Google today, is because you guys had something that was very applicable. It needs to be fast. Needs to use all those features from NCAP for working with our infrastructure, and we also need to have filtering methods that we can plug in and developers can use so that we can keep up with the tide. And Robert, we gave a lot of this to Robert, and Robert pretty much picked it out, and he created nmessage. So now we're going to switch over to Robert. All right. You want to take my yellow?
Yeah, you have to switch cables.
I was doing 800 by 600, but we'll see if whatever you have works.
So something Eric had reminded me of this from RFC 1034. The sheer size of the database and frequency updates suggests that it should be maintained in a distributed manner. Approaches that attempt to collect a consistent copy of the entire database become more and more expensive and difficult, and hence should be avoided. In 1987. Well, fortunately, we like doing expensive and difficult things.
Well, he was talking about the hosts.txt
Yeah,
file.
that's what. Yeah.
Yeah.
Well, in this case, we're collecting all of the host names.
Okay. I'm with you.
Let's see here. So we have this in-message file format, which is the successor to the NCAP packet capture format. And the idea is that we're not only capturing packet information, but also things that are not necessarily best represented as packets on a wire or datagrams on a wire. So the idea is we don't know what types of information we're going to store, so we should make it store opaque blobs of information. And perhaps at runtime, we'll load a module and be able to learn how to interpret that blob. So we have blobs on the order of 10 to 10 kilobytes in length. We probably don't want to optimize the transmission of DVD ISOs on a UDP broadcast network. We're interested in things like DNS and email and HTTP, things of that order of size. We decided to optimize for UDP over jumbo frame Ethernet in order to minimize the number of socket receives that have to be done to read a particular quantum of data. And turns out that Google has a ready-made encoding format called Protobufs. It's essentially an extensible binary wire format for encoding fields of data, primitive types, integers, floats, byte arrays. Unfortunately, Protobufs are not self-delimiting and they're not self-describing. So we have to add some additional framing and some additional intelligence in order to be able to use that for our UDP broadcast medium. And for the protocol engineers, this is essentially a description of the protocol. So we have a constant length header vert and a variable length vert, which can encode one or more payloads. So the NCAP format captures one packet and represents one packet when it's rebroadcast. But since we're batching that data, or we're buffering that data, we can pack more than one payload into a jumbo Ethernet frame. So the average DNS packet is probably less than 512. We can fit perhaps 16 of those into a jumbo frame Ethernet packet, or even more. So why not minimize the number of socket calls, system calls that you have to perform in order to read that data off the network? What if your payload is larger than a jumbo frame Ethernet frame? We should be able to fragment that. So I'm sure you've seen spams, emails that are longer than 8 kilobytes. So we want to avoid having to have a truncated bit that indicates this blob has been truncated and you'll have to deal with that. Well, we can just fragment the payload, and the receiver can reassemble it and pass that reassembled payload to the client application. And we avoid, let's go to the custom header part. So there's a 4-byte magic value at the beginning of the frame or beginning of the file buffer. Flags octet, and there's a bit that means fragment, there's a bit that means compress. There's a version octet, your version is 2, and we can represent up to about 4 gigabytes of payload. We've not come anywhere near to that limit.
Nope.
So fragment, there's a bit that says fragment. We fragment into multiple frames. The receiver has to reassemble it. And we cannot use IP fragmentation because that limits us to 64 kilobytes. So we do the fragmentation, the segmentation, and the application layer, much like TCP. There's a bit that will compress the data, so we can fit even more DNS data or email data into a given Ethernet frame. And if you see both of the bits, then you compress it and then fragment it, because doing it in the other direction, in the other order is
Problematic.
well, you won't use the maximum. You won't use as many bytes in the frame if you fragment and compress. So the payload header, this is the variable length part and is now encoded using Google Protobufs. There is a vendor ID and a message type. The message types are per vendor, so if you want to create your own payload message types, we would assign you a vendor ID, and you can assign whatever message type values you want. A timestamp, 64 bits seconds plus 32 bits nanoseconds, so you get a nanosecond precision timestamp. And we have a few optional fields for classification, source, operator, and group. So cooperating senders and receivers can further classify their data. And the payload itself, this is the opaque blob of information. Each WinRD message type tuple will identify a particular unique type of message. And we don't necessarily require that the blobs be encoded with GPV, but they frequently are. And we optimize for that particular case. So now we have the libinMessage C client API, and this is client applications that want to process, send, receive, read, write, set up, multiplexing, demultiplexing, all sorts of topologies with their in-message payloads. We include both a simple single-threaded interface, and we have a multi-threaded Octopus I/O engine that you can utilize if you want. The multi-threaded code is good in that we could spread the load across multiple CPUs when we decode those packets, those messages. And if you happen to have a chunk of code that processes those messages, and you make it reentrant so that it can be called at multiple times from multiple threads, you get whatever speed up is possible from that. We're currently developing Python and Perl bindings. The Python bindings are stabilizing. We haven't yet made a stable release of the Python bindings yet. And Matt Sisk at CERT is working on the Perl bindings because I do not use Perl.
Showing his age.
Well, Python is probably just a few years younger than Perl, but there's also a message module interface so that we can extend the message types that the library understands without having to recompile it and relink all of the readers and writers. So essentially this is a DSO that exports a particular structure and fills in particular fields and may optionally provide function pointers that perform a specific processing on specific, pretty-printing, parsing, that type of.
So, for example, DNS.
Yes, DNS has a variety of interesting and particular wire formats for its data fields. There's the traditional label, octet label encoded name, which is, I believe there was a security vulnerability recently based on this concept in the SSL certificates that happened to have embedded nulls in the labels, which is valid according to the DNS wire protocol. So there's an ISC DNS message type that will provide a specific function to turn a label encoded DNS name into a human readable, dot delimited name, and we don't want to put that type of logic into libinMessage. We want to push that out into a plugin for that particular message type, since we try to make the core library as agnostic of the upper layers as possible. And typically the message module is a fairly short amount of code that usually just glues some generated object code from the Protobufs compiler. So we make it, this allows additional complexity that we keep out of the core library. And that's the end of my presentation.
Cool. This is all available online. You can download FTP from the ISC website, and you can actually see some of the descriptions we had. ISC is vendor ID 1. If you want to start using this yourself, you can make yourself a vendor ID.
Well, no, you would ask us for vendor ID.
Oh yeah, yeah. Everyone just picks their own.
We'll be number one.
John Purcell isn't moderating that anymore. Register it with us, and we'll make sure that in the source code that everyone will play nicely. So now that we have in message, we now actually have some new channels that we can make available to people. Spam. We have a bunch of spam traps out there, and there's actually another provider that's sending us this is spam reports We basically take all the envelope information, some of the headers, extract some URLs out of it, and then packetize that, and people can actually use that. A search provider has given us some URL link pairs so that we can actually, if someone wanted to, they can actually make a map of here's the normal web, and then if it's not in that, maybe you want to spend some special attention to it. NetFlow is actually packetized. You can actually, we don't do anything with that. NetFlow already has its own set of tools, like the Silk toolkit. People are aware of Configure. We got ourselves involved a lot with that and helped aggregate and collect a lot of the data that was going through the sinkholes. So we created some types that we had all of the web servers report in, and we also captured the DNS data, and we actually captured some of the P2P data, and we created channels for them so we could actually have people see that stuff coming in real time. We are making some development work for malware. I might describe that more on another slide. We're also getting some darknet feeds from ourselves and a large ISP, and we expect to be getting some more. And that's just normal packet stuff. It's not necessarily end message. We might choose to create an end message module to describe stuff. Particularly with malware, you might start with hashes or MD5s. At another layer, above that, you might have people passing around, I'm interested in this, or I saw this too. And then above that, you might have something more descriptive, maybe even encapsulate some XML, as IODEF is very popular with that.
Is the NetFlow channel so it's just a single blob that has all forms of NetFlow, SFlow, or is it a single version?
We have some version 5 just from our own routers, but getting NetFlow from other providers has been difficult. It is not an active channel. But yeah, I would expect that SFlow version 9 is pretty much the standard for that because it does IPv6 and all that other stuff. Some other people are working with NetFlow and using it combined with passive DNS. But we're not doing any of that development ourselves right now. There are already tools out there. So for passive DNS, you can sniff stuff off the wire. That .255 just basically typifies that there's a channel number that's 202, and here's the broadcast address, and we're listening on port 8430, where all these packets are spitting out there. And you'll see some information like the timestamp. There's the type, ISCN cap, the identifier of the sensor operator who submitted it, which is kind of randomized and kept separate, but you can kind of tell where the data is coming from one source. There's the name server that it came from. Our name server I commented out. That's the sensor operator, so you can see where it came in. And some of the flags that go with it. The first part is the answer part. Or actually, the first one is the query. The 0 means that there was no answer, but then it told you where the name servers were in the name server section and additional info. They'd actually hand you the IP addresses. So you can take all that and you can put that into a structure if you're using libmessage. But you can even just do plain old text processing based on that.
You should use the library.
It's much more efficient.
Don't parse arbitrary text.
But some of us old timers use awk, sed, Perl, and such, and don't keep up with that. So some people have done some useful things without being efficient. But yes, do take the time to actually learn to C or Python or whatever API is out there. You'll save yourself some money on your hardware. So another one, here's a sinkhole for Configure. So here we have another type, for ISC HTTP, and so we get where the request came from. So these are people who are infected who are coming back to try to talk to their command and control over the web, and we just happen to take over the domain that they're using for that. So we can kind of do some things. We do some POF. We look at all of the stuff that we can get out of the request, and that would help identify for which particular strain of Configure they were infected with. And then we can create a database. People can use some of this data for remediation tools, and some people do. Chris Lee did a lot of work. Was out of Georgia Tech, now a Shadow server. put a lot of that together and make it useful for people. So for spam, we do a bunch of pre-processing scripts that basically take the email message, out of your standard input and then extracts the things that people are interested in. This would be the hello from RCPT2, the IP address it came from, the received headers, and the URLs that are found in the message. No one's really interested in the image blobs yet, but if someone does become interested, we might do something with it. We have plugins for postfix and QPSMTPD, which is a Perl tool, which is actually very fast and efficient on Linux and BSD servers. So we have several spam traps of that type, where it's just basically taking unused domains and people will just keep sending spam to it anyway. They're seeded or populated. And that's very useful because that really is spam. We have methods where you can actually tag, this is spam report. So if someone has a reporting address, an abuse address, or if they have a button they click on their client, we can actually create packets that say, here's a user report. Now you have to go a little statistical because there are false positives in that some people may take some marketing and say it's spam when it may not necessarily be pure spam. Something we haven't implemented yet but would be interesting would be, say, as every mail message comes in, take the headers from that or the envelope info and say what spam assassin score was with it. And then you can basically, if you have everyone reporting into a central source, you have a really good chance of real-time reputation. Maybe that some commercial services have and might be able to do a public domain one. All of this spam is a great starting point for analysis. You'll typically find that people are using botnets or in some cases even just buying services off of bulletproof hosting. It'll lead you to some other data. Here's an example of some spam you get off of the spam channel. Again, the timestamp and the type and the sensor. It's a spam trap. I obfuscated some of this, except that's a real domain. And there's a URL in there, that ff24490.gif. Well, it points to basically a Viagra Vioxx, kind of advertisement. So this is obviously some kind of bad domain that's being used for phishing, or actually, in this case, just spam. So one of the things we do is we take some of the passive DNS that we have in there, and we look up that domain. It points to an IP address. Well, lo and behold, here are all the other domains that are being used by that IP address that we've collected via passive DNS. So once you find one, you can actually do blocking or add blocking on all the other domains even before they're used. Like maybe they don't use them all right away. So you can actually start to be proactive. You can find some other information like that jw.ru is probably something close to what the real name for that server is. And then you can go probing around though and find some stuff. When you have multiple data types like passive DNS or spam or other information about the networks, you can do a whole bunch of data combining and find some more interesting info. Jose Nazario and Thorsten Holtz, back in Malware 08, they made a paper where they created a point system for all these different things. When you combine them together and add up the points, you actually say, hey, that's a fast flux bot. Like being on multiple networks within the IP address ranges, or how often or how many hosts do you have in the A records. Dave Dagan and Wenki Lee, they just basically took passive DNS, a little bit of string matching, like looking for the word antivirus inside of the packets coming by, and they were very fast and successful at finding fake AV sites even before they were blacklisted by other services. Richard Clayton is a professor who was investigating a lot of the censorship that's being done in the UK. So he takes a list of hosts out of passive DNS, combine that with some active scans that he does himself, and he can pretty much determine which are the URLs that were getting blocked, including at one point Internet Archive, which is a pretty heavy website to be blocking. Andrew Freed, he's a consultant with us. He's going to be talking at Black Hat DC in January about a lot of the stuff that he did of combining the spams, the BGP info, passive DNS, analysis of some top-level domain zone files to basically go after things like Zeus Avalanche or phishing or whatever. He's very active in the community and just saying, hey, here are all these new domains. They get stuck in the serval and they start to get blocked. But he used to do this full time for the IRS back when they were having phishing problems, and now he's actually helping not only the IRS but all these other people who are getting hit with a lot of the same methods. Ed Stoner works with CERT, and at FlowCon in January, he's going to be talking about how he puts together passive DNS with NetFlow to help expand on what botnet knowledge you already have. You can already get some botnet knowledge out of NetFlow, but if you take passive DNS to the next level, you can basically use your IPs to help find more names, which will help you find more IPs, which will help you find more names, and eventually get a map of everything. We're actively looking to start the malware channel. Some other people are creating products for DNS reputation based on the data. We're interested in perhaps offering scanning because people who are doing scanning right now for DNS, they're finding that the bad guys are figuring out who they are, so they're getting blocked. So we may offer some scanning infrastructure for people. Automated abuse or distributed denial of service attack reporting might be a way to standardize and have some real-time reports of saying, hey, I'm getting flooded, and then you tell a whole bunch of other people, which might include your antivirus vendors or ISPs directly, and as opposed to picking up a telephone. With the URL search data, you can perhaps find that a whole bunch of people are coming to some place at once, and that might be because Britney Spears did something that day, or it could be that there's a new virus that everyone's downloading at once. But if you have everyone looking at a new URL all at once, you can perhaps take a look at that. And BGP updates, that's security data as well. That can be helpful for finding out people's networks getting stolen out from under them. And here's how people can help. If there's sharing methods that people are using right now that are between themselves, and they want to incorporate more people into that, we can help reduce some of the overhead by having it put in one central place and using our broadcast infrastructure to get to all the people who need it, not have to resend or recopy that data between multiple places. And if you don't like working with service agreements and NDAs and stuff like that, we can help simplify things. Something else you can do is bring some servers to SIE and actually take a look at what's out there. I mean, there's a lot of good minds here at Google. I can imagine some of them might be interested on the security side of seeing what's out there and seeing what they can figure out and see if they can combine it with some of the data that you guys already have. You can also install sensors, particularly with ISPs or corporations or security companies. Everyone's got some kind of data that is perhaps worthless junk to them, but to someone else, they can do something effective with it when they combine it with something else. So if people can go ahead and send us more data, we'd appreciate it, and so will the rest of the security community that works with us. So we're SIE. You can send us email. That info will get to all three of us. We got a website. There's my phone number. And for end message, you can go and download it yourself. We have a developer mailing list that we recently set up where people can talk about how they use it. This is generic. It's open source. This is not SIE specific. You can use this stuff internally and then tell us how you're using it. It might be interesting. NCAP's available from us as well. We thank you guys for making Google protocol buffers, and we especially thank all the sensor operators who are out there donating data to make all this useful.